Welcome, class 9. Today's topic is linear momentum and Newton's second law of motion. So, let's say that there is a car, and this car has some velocity and it is moving in a particular direction. Now, in order to stop this car, you will require some amount of force so that the car can stop at a particular given point. Similarly, if there is a truck which is heavier and has more mass than the car, then again, in order to stop the moving truck, you will need some amount of force again so that the truck stops within the given frame of time and within a particular point. So, here the amount of force required in case of car and in case of truck to stop it, in the amount of force required will be more in case of truck. We all know that, right? Similarly, if you have a tt ball which is again moving at a certain speed, and there is a cricket ball which is again moving at a particular speed. Now when you try to stop, or if you get, if the ball hits you, whether it's the tt ball or the cricket ball, in which case do you feel more impact of the ball? Will it be tt ball which will hurt you more, or will it be the cricket ball which will hurt you more? So the answer is the cricket ball, because it has more mass. So the force needed to stop a moving body in a definite time depends on two factors. Number one is its mass, and number two is its velocity, the velocity of the body and the mass of the body. That's why, in comparison with a car and a truck, more force will be required in order to stop the truck compared to a car. And similarly, if you have a tt ball and a cricket ball will have more impact when it will hit us, because it will have more mass. So here the mass and velocity are the two factors, and if you multiply this mass and velocity, the product that we will obtain after multiplying is called as linear momentum. So we can define linear momentum as the linear momentum of a body is the product of its mass and velocity. And the linear momentum is represented by small letter p, which is equal to mass into velocity, which is represented as m into v mv. So p is equal to mv means linear momentum of a body equals mass into velocity. So unit of momentum is equal to unit of mass into unit of velocity. So SI unit of mass and velocity will be SI unit equals unit of mass is kg and unit of velocity is meter per second. So simplifying this, you'll get kg meter per second. That will be the SI unit of momentum. And similarly, the CGS system, in CGS system or CGS unit, the unit of mass is grams and unit of velocity is centimeters per second. Therefore, the unit of momentum will be gram centimeter per second. Now let's learn about change in momentum. A change in momentum in physics, we will say that a small change can be represented by the Greek letter delta. So delta P, or simply del P, means small change in momentum. So since P is equal to mv, we can say delta p, that is the change in momentum, will be equal to change in m into v. Now, since mass cannot be changed for a given particular object, mass remains fixed. So we cannot change mass. Therefore, in order to change its momentum, we can change the velocity. So the change in momentum will be better represented as m, because mass cannot be changed. So mass remains as it is, but velocity changes. So delta p is equal to m delta v. This means that the change in momentum is equal to mass into change in velocity. So in change in momentum, mass remains same, but the velocity changes. Next, rate of change of momentum. So whenever we say rate, that means we are referring to the time limit. Okay, so if we limit the time, that means if we uh, apply the change of momentum with respect to time, then rate of change of momentum can be represented as change of momentum with respect to time, that is uh, change of momentum by time. Since change of momentum is represented by delta p and time with respect to change in time will be delta t. So delta p by delta t is the change of momentum with respect to time is equal to delta mv by delta t. So this is momentum with respect to time. So this is also momentum with respect to time. Now since mass cannot be changed as we have said earlier, so mass remains constant, that is it is not changed, but delta v, that is the change in velocity takes place with respect to time. So m into delta v by delta t can be written as m into delta v by delta t. Now delta v by delta t means change in velocity, that is we can say with respect to time is rate of change of velocity. Now rate of change of velocity is better termed as acceleration. So delta v by delta t can be represented as a, that is acceleration. So in this expression we will exchange or substitute delta v by delta t with a. So we'll get delta p by delta t is equal to ma. That means delta v by delta t is substituted by a. So delta p by delta t is equal to ma is the required expression from rate of change of momentum. Now the acceleration produced in a body is always directly proportional to the force applied on it. So we can say acceleration A is directly proportional to F. And this relation can be shown with the help of a graph. Okay. So here the graph which is plotted against force versus acceleration. So this shows that the acceleration is directly proportional to force. This means as the force increases, as you see the graph, as the force increases, the acceleration also increases. That means more force you apply on a body, more acceleration can be observed. If you apply more force, then more body can accelerate. So that's why force and acceleration, they are directly proportional. So here this is the graph showing acceleration versus force. Again, the force needed to produce a given acceleration in a body is directly proportional to the mass of the body. So force is directly proportional to mass. This means that more the mass, more the mass of an object, more force will be required in order to accelerate that body. So if the body is of 1 kg, you may require a certain amount of force in order to accelerate it. But if the mass of the body is, like, for example, if it is 10 kg, then more force will be required in order to accelerate that body in the same amount of acceleration. So force will increase in that case. So force increases as the mass of the body increases. And similarly, if you make the graph, then again, as mass increases, the force also, required force is also increased. So this shows that mass and force are directly related. So this is the graph showing force versus mass. Next, the acceleration produced by the same force in bodies of different masses is inversely proportional to their masses. This means that if the same force is applied on different bodies, okay, different bodies of different masses, then the acceleration produced by the same force will be different. That means the same force will produce acceleration on heavier mass, less acceleration, and the same force if applied on the lighter mass of the body, lighter body, then it will produce more acceleration. So in this case, if the mass decreases, then the acceleration increases, or if the mass increases, then acceleration decreases. So here they are inversely proportional. So when it is inversely proportional, then you will obtain this kind of graph where it moves towards the, it moves negatively like this. So as the mass increases, you will see the acceleration decreases, it goes down. So this is the graph showing acceleration versus mass. So now we can come to Newton's second law of motion, which states that the rate of change of momentum is directly proportional to the force applied on it, and the change in momentum takes place in the direction in which the force is applied. So since we are talking about the force and the rate of change of momentum, so from Newton's second law of motion, we clearly can say that force is equal to rate of change of momentum, that is del P by del T. Now since del P by del T, earlier we have derived that it is equal to the product of mass into acceleration. So force is equal to mass into acceleration. F is equal to ma is the relation that we obtained from Newton's law of motion. So this means that force is the product of mass and acceleration. So this simply means that if force is equal to mass into acceleration, and if the force is equal to 0, that means if no force is applied on a body, then the mass cannot be 0, since in mathematics we see that if this is 0, then either this or this has to be 0. Now mass cannot be 0 for a given body. That means acceleration has to be 0. So if F is equal to 0, then acceleration A becomes equal to 0. This means that if no force is applied on a body, then the body will have 0 acceleration. This means no acceleration will take place if there is no force applied on any given body. So we can understand from this that a body not acted upon by any external force does not change its acceleration. That means does not change its state of rest or of motion. And this is Newton's first law of motion. So from Newton's second law of motion, we also get the proof of Newton's first law of motion. And also, since force is equal to delta P by del T, that is the rate of change of momentum, since force is equal to rate of change of momentum, that is delta P by del T, if we cross multiply, then we'll get that delta P is equal to force into delta T. So for a given momentum, linear momentum, either the force if it is increased, then delta t, the time will decrease. Or if you decrease the force, then the time duration has to increase. So for a given linear momentum, large force is required in small interval of time. That means if you increase the force, then delta t has to come down. That means this time interval has to be small if the force is large, or just the opposite. If small force is there, if you apply a very small force, then the time duration has to increase. That is, it will be a long interval of time. So let's see few examples of large force with small interval of time. So if you apply a large amount of force, then the time required will be very less for a given momentum. So example is, when you are hammering the nails, you are applying large amount of force, and that in a short interval of time. So that is creating equivalent amount of momentum. Also, second example is when a batsman hits the ball, is applying more amount of force out here in a very less amount of time. So that will create again equivalent amount of momentum, linear momentum. Now let's look at the second part, that is example of small force in long interval of time, so that the linear momentum remains as it is. So you are applying less amount of force, but the time duration is more. Number one example is, while catching a ball, the cricketer withdraws his hands along with the ball. So in order to catch the ball more effectively, the force cannot be applied more over here. So the force will be applied very less, but the time interval, if it is not increased, that means if while gripping the ball, if the cricketer does not withdraw his hands along with the ball, then that time duration will not be more. If the time duration is not long enough, then with very small force you cannot stop the ball. So in order to stop or catch the ball, by applying very less amount of force, you have to withdraw the motion of hands along with the motion of the ball. Number two is, athletes often land on sand or foam after taking a high jump. So in order to decrease the impact, the force has to be less. If the force is if the force is decreased, then the time duration has to increase. So the time duration is increased if the body lands on soft objects like sand or foam, so that the impact becomes less. Or if the impact is more, then the athlete may hurt himself or herself while they come in contact with the concrete floor. Third example is, when glass vessels fall on a hard surface, they break. Okay, this means that if they come in contact, if they fall on hard surface, they will break. That means the force is the force is more, and the impact is so short, the time duration is so short that it breaks. But if the force is in order to reduce the force, if it lands on any soft object, so that the time duration is increased, then the glass vessel will not break.